Let's start with a wild thought. What if one of the most basic things you learned in physics is just wrong? Seriously. We're all taught that the universe is made of tiny little balls of stuff. Electrons, quarks, photons, particles. But today, we're going to dive into a radical new framework that says the particle itself isn't a fundamental thing at all. It might just be a kind of useful illusion. So get ready, because we're about to rebuild physics from the ground up, starting with a problem that's been bugging people for over 100 years. Right, so the whole mess begins with this classic headache called wave-particle duality. You take one thing, say an electron, sometimes it acts like a wave. It's spread out, it's continuous, it can interfere with itself, but other times it acts like a particle. It's localized to a single point, it's discrete, it hits a detector with a definite thwack. I mean, these things are total opposites. One is kind of everywhere at once, the other is right here. How can it be both? And that really is the question, isn't it? How can one thing embody two completely contradictory sets of properties? For decades, the standard answer has basically been, well, that's just how it is. Deal with it. We're told to just accept the quantum weirdness. But what if we don't have to? What if the problem isn't reality, but our starting assumptions? What if we've been asking the wrong question all along? Okay, so let's try a totally different approach. We're going to throw out our assumptions about particles and waves. We're not starting with things at all. Instead, we're going to build our physics up from a single powerful idea, a single principle. And that principle is called recoverability. The whole game here is to see if we can derive all the bizarre rules of quantum mechanics just from this one concept. So what on earth is recoverability? Well, think of it as a test for what gets to be called real. Imagine you build a sandcastle. If a tiny wave washes over it, but you can still see the shape of the castle, it's a recoverable structure. It's stable. But if a big wave just flattens it completely, wiping out all the information about its shape, well, it wasn't a very robust configuration, was it? In this new picture, reality is stability. A thing is real if it can take a small hit and not fall apart. Now, to make this work, we have to totally reboot our idea of phase. Forget the image of a wave going up and down. That's not it. In this model, phase is more like an abstract bookkeeping tool. It's a label that lets us keep track of all the different paths or histories a system could have taken and how they relate to each other. It's not a physical thing waving through space, it's just information. Okay, so this gives us two totally different ways to describe the world. First, there's PyQ. Think of this as our wave regime. It's like watching a 4K high-definition video that captures all the possibilities, all the nuances, all the interference. But what happens if that video file gets corrupted? If a bunch of data gets lost? Well, then we're stuck with PyE. This is a much cruder description that only shows us the big, chunky, stable outcomes that survived the data loss. And that, my friends, is our particle regime. So if we have this beautiful, high-def, wave-like description, why isn't the world always like that? Why do we ever see particles at all? Here's where it gets really cool. The principle of recoverability itself forces there to be a boundary. There has to be a point where the continuous wavy description simply stops working, a point where the wave must break. You know how in regular quantum mechanics, collapse is this mysterious event where a wave just magically turns into a particle when you look at it? This idea throws that out the window. Here, collapse isn't some special magical event, it's a viability failure. It's the point where an interaction is so messy that the delicate phase information, our high-def video, gets scrambled beyond repair. The wave description isn't a valid way to represent the system anymore, so it breaks. And this leads to this beautiful, simple piece of logic. Just follow me here. We know for a fact from experiments that wave-like interference happens. It's real. So let's work backward. If any tiny disturbance could destroy our phase information, we'd never see interference, ever. It'd be impossible. But we do see it. Therefore, there must be a safe zone, a minimum threshold of disturbance that a system can handle without its phase information being totally scrambled. Let's call this threshold kappa. This quote really nails it. The simple fact that a stable, wave-like regime can even exist forces there to be a boundary. And on the other side of that boundary, where phase information is lost, our description has no choice but to become discrete and chunky. See what happened? Discreteness isn't something we assumed at the start. It's a consequence of information loss. All right, so we've established this safe zone, this stable playground that exists below the kappa threshold. The obvious next question is, what are the rules in there? What kind of math governs how things evolve in this protected, phase-capable world? And the answer, once again, is forced on us by our starting principle. In order for all that phase information and those delicate interference patterns to be stable and recoverable, the rules of evolution have to be linear. Any kind of nonlinearity would just mix everything up in a way you could never untangle. It would violate recoverability. The system has to play by simple, additive rules to survive. And this is what linearity looks like in math. All this equation is really saying is that you can take two possibilities, add them together, and then see how the combo evolves. Or you can evolve each one on its own first and then add the results. You get the exact same answer. It's this simple property that keeps everything nice and tidy and recoverable. And here is the absolute knockout punch. Once you demand that the rules have to be linear and they have to preserve stability, you find yourself backed into a corner, mathematically. There's basically only one kind of equation that can do the job. And when you write it down, you get the Schrödinger equation. I mean, this is huge. We didn't just find it in a textbook. We derived the fundamental equation of quantum mechanics just from the idea of recoverability. Okay, so that's the story inside the safe zone. But what happens when an interaction is too big? What happens when we cross that kappa threshold and our lovely high-def pi-q representation just shatters? What's left over? Well, when all that detailed phase information vanishes, you can't just be left with nothing. Something has to be conserved. The only thing left to keep track of is a kind of total reality budget, a quantity that was being conserved all along in the wave regime. It's the one piece of information that makes it through the collapse intact. And this completely changes how we think about probability. I mean, think about it. We only ever use probability when we're missing information, right? You talk about the probability of a coin toss because you can't track every single detail of its spin. This framework says that's exactly what's happening in quantum mechanics. Probability isn't some weird fundamental feature of the cosmos. It's just what's left when our high-def representation breaks and we're forced to work with incomplete information. And now, we can finally put all the pieces together. We've built a world from a single principle, we've derived its rules, and we've seen what happens when those rules break down. We are finally ready to answer that very first question. What is a particle? There it is. That's the core idea. A particle is not a fundamental little nugget of reality. A particle is a residue. It's the stable, chunky pattern that's left over for us to see after the richer, more detailed wave-like description has fallen apart. Okay, let's break down that formal definition. It sounds complicated, but it's not. Minimal, stable, interaction outcome. It's saying a particle isn't a thing, it's a reliable echo. It's the click you hear in a Geiger counter. The click isn't the thing itself, it's the stable, repeatable evidence that an interaction happened. The particle is the pattern of the click. And this just changes everything. So why do particles seem discrete and chunky? Because our low-res pi description literally cannot represent continuous information. Why do they seem to persist, leaving tracks in a cloud chamber? Because what you're seeing is the same stable, invariant pattern being triggered over and over again. And things like mass and charge, they're not properties of a little ball. They're just labels we use for the specific, conserved behaviors that define that stable pattern. So let's put the old idea of a particle to the test. How does it stack up against our foundational principle of recoverability? Yeah, not so great. As you can see, the classic concept of a particle as a fundamental little thing fails on every single count. It's not recoverable, you can annihilate it, it doesn't have a persistent identity, and it's definitely not independent of our representation. In fact, it only really shows up when our representation breaks. So here's the final verdict. The idea of a particle as a fundamental object is an incredibly useful illusion. It's a great tool for doing calculations and describing what our detectors see. But it's not the bedrock of reality. It's the residue. It's the shadow that's left over when the light of our high-definition, phase-capable reality gets blocked. And that, of course, leaves us with one last mind-bending question. If particles, the things we thought were the absolute bedrock of reality, are just a kind of shadow, then what is truly fundamental? What's actually real? This framework suggests the answer isn't a thing at all. Maybe what's fundamental is a principle, the unwavering logic of recoverability and the stable patterns of interaction it allows.